Hey there, this is Seth Schaefer of Team Just Cause Robotics, and today I thought that I would do my CNC video a little differently from the first parts and talk a little bit of the cam side of this. Last two videos I pretty much just showed the CNC running and talked about what I was doing to some extent from the actual physical moving and setting up of the parts and flipping them for different orientations of the setups. But here I want to talk a little bit and give a bit of a better sense of what the software side of things is like in actually programming the cam for the parts, especially these complex multi-setup and several tool change parts. So this is by far the most complicated part that I had in the robot to machine, and you can probably see why. Not only did this part require 4 separate setups to machine on 4 faces of the part, but just this one face required doing 5 tool changes. So I start with this tool, switch to that tool, switch to that tool, switch to that tool, switch to that tool, and then switch to this tool for both of these operations. And then over here, I was able to get away with just 2 different tools, and here I have also 3 different tools. So the top and bottom I wrote as one setup because when I flip the part, as long as this side stays in the same position, it's exactly the same. These holes end up being exactly the same on either side as long as they're symmetric about the correct axis, which would be this one. So if I flip the part such that this end is facing that way, then these holes would run the opposite direction on the other side, and that would be terrible. But as long as I flip it about this axis, so I flip it that way in the vise, the holes would line up perfectly. So to start out with, I program in a setup which requires not only knowing what the part's finished version will look like, at least with respect to that face of the part, but also what the stock looks like. So in this case I was starting with a 3-inch tall by 1/2 inch wide, which is the final dimension, by about 10.75 inch long piece of aluminum 6061 bar stock. The final dimensions for the part are a bit shorter than that overall, still 1/2 inch thick, but with lots of pocketing and stuff. And then also, this dimension here to here is 2.2, whoops. This dimension from here to here, 2.25 inches, and from here to here is 2.75 inches. So I have to reduce the height of both sides by a minimum of 1/8 inch overall to end up going from 3 inches to 2.75 inches. And I'm also pocketing down here by 1/4 inch all the way throughout. And then I'm drilling all these holes, which requires me to not only drill, but also to spot drill first. So here, when I highlight over these, you can see what the tool is actually doing. So these are both things that involve the same exact tool. In this case, this is a 3-flute 1/2 inch flat end mill. And then I switch to a spot drill, which is actually a chamfer tool that I'm using as a spot drill. And then finally, drill, also known as a jobber length drill, which is like a standard drill bit you'd get in any drill bit set you might buy at the hardware store. The reason I have to spot drill first is because jobber length bits are quite long compared to their diameter, so they're not stiff enough to stay on center when you just straight drill into a flat piece of material, so you really need a drill point already in the material. Oftentimes if you're working by hand you might just punch it in with a center punch, but in the case of CNC there isn't really a good way of doing that other than just using a tool that has an angle to the tip. So using my chamfer mill / countersinking bit was the best way to go about that. At the time of making this part, I had exactly 6 tool holders, so in creating just this one part I had to use all of them. That's why I don't have a dedicated spot drill, even though I do own one. I'm just going to reuse the same tool here so that I can use it again here for spot drilling on this side. Alright, anyhow. On to the actually exciting part, actually cutting the part. So there's a couple different things that need to be done in the setup. First off, you have to define what the stock starts as, but second off, you have to define the coordinate axes and your datum. So the datum is the point at which I was actually referencing in the machine as the 0, 0, 0 point. So in this case, I use the stock top as my Z0, which I do for practically all of my parts. There are only rare cases in which that's not beneficial. And then my x-axis is basically like the long axis of the machine table, and the y-axis is away from me towards the machine's like Z column. So x is positive to the right, and y is positive away from me, with z being positive upwards. In other words, I'm starting at z0 and cutting down in the negative z direction for all of my passes, and pretty much every movement of the machine is going to be in the negative y and the positive x, because I'm not really doing any machining to the left of where the stock's leftmost edge is, or to the like farthest point away from where already the farthest point is. And again, I use basically a vice corner, or in this case I actually offset that vice corner by 2 inches using a 1, 2, 3 block to like line up that edge of the stock so that I could repeatedly find it when I'm swapping in a new piece of stock. The most efficient way to do parts like this is to always have your setup be the same as long as you can keep it that way. So every time I would do a top and bottom of one of my parts, and I made this part I think 3 times, I pretty much would, well, I tried to do it 4 times, but I think I ended up screwing up one of them. In any case, I would stick it in the vise, find the Z, and then do all 3 of them, then flip them over, find the new Z, which was again an 1/8 inch lower than before, or whatever, and then do all of the top and bottom operations again. And then, when I had to do the 2 different faces, the Z's would be the exact same, so I wouldn't have to worry about that because the part was a 1/2 inch tall either way. But I did have to actually I did have to make sure that I was referencing the correct point for my datum for each of those. So you can see here, I have to flip it the correct way again to make sure the datum ends up in the correct place. And also, because I had milled these faces in, I actually kind of needed to not use the vice corner anymore because I had to offset it back by a 1/4 inch, since the vice surfaces would be gripping here and here instead of at the stock dimensions that are shown this way as being 2.75 inches. I could have done some more elaborate stuff in the design for this, where I created a stock body that was the actual shape, but it was like not worth the effort for doing that, to just like slightly uncomplicate the cam, but require me to spend a lot more time actually setting up in the first place. So yeah, so for the top and bottom, I use the 1/2 inch bit, and I pretty much just face off the whole thing by an 1/8 inch, and then I come in and cut out this pocket, and then I spot drill and drill. These holes would be tapped eventually for 1024 screws. And I can simulate this happening so you can see exactly what's going to happen. So green is the stock, this simulates the flutes of the cutter, and you can, this is not real time, I can speed it up or slow it down however much I want. So you can see it does this kind of weird pattern, and then it finishes up the edges, and then I have the spot drill come in, and then I'm doing peck drilling, which allows it so that the chips don't clog inside the hole. And that's pretty much that. And then I don't show it doing the same thing on the opposite side, but in reality I would have it do the same thing on the opposite side. Next, we have the motor side set up, so that's this one. So here, I'm going to be pocketing out this deep pocket with a 1/2 inch end mill. I'm using adaptive because it's by far the most efficient way of preserving tool life, and also it basically just keeps really consistent cutting forces on the tools, which means that your chances of breaking them are much lower, and you can still get pretty good material removal. Then I'm coming in with this 1/8 inch end mill, and I'm doing all of this pocketing out that I need to do for ventilation for the motor, and also for where the screw holes for the motor will be, so that I can actually mount it in the robot. And also these larger pockets allow the actual wires for the motor to be fed through them. Now I am spot drilling like you saw before. Let's speed this up a bit. Now I'm doing more drilling for the larger holes that get tapped for 1024, and then I drill even bigger ones for quarter 20s. So this is spot drill. These are actually, these are the, oops, that wrong. So this drill is the spot drill. Then this drill, I believe, is the pilots for the 1024. No, this is pilots for quarter 20. That's why it's the larger one first. And then this is pilots for the 1024. And then I have boring operations here, which essentially just give me these recesses and counter bore where the shoulder bolts will go. So that's a counter bore for a shoulder bolt, counter bore for a shoulder bolt, counter bore for a shoulder bolt, and then a slight recess for what I had originally designed in as being aluminum spacers, but ended up switching to 3D printed nylon. Now we come over to the final side, which is the non-motor side, where I have all of this weight reduction pocketing happening. Here, it's basically less critical that everything lined up like before, but I am also cutting in these edges. So you'll see that coming up first. So first I'm starting at the 1/2" tool again, just kind of cutting in those edges there. And then I clean them up with contour passes. And now we're doing some more adaptive clearing. Do bulk material removal here. The tool doesn't quite fit with an adaptive here, so I had to use a normal pocketing operation, which is a bit more aggressive on the tool, but such is life. And then I clean up all the corners to make them as sharp as possible and remove what little weight that I still can, using a smaller tool, which is a 6mm end mill. And then last but not least, I clean up all of those edges with contour pass with the same 6mm end mill. So if I were to simulate the whole thing, start to finish, again, the top and bottom, it'll only happen once, but in real life it happens twice. This is what it looks like. So yeah. And I can also hide the original model, so you can see that it is in fact going to remove all the material in exactly the places that I want and nowhere that I don't want. So yeah, that's pretty much all that goes into making this particular part. Now let's watch the CNC actually cutting it out.